of the lattice. In the y dimension, let's think about that as being infinite. And then I can, so ky is a continuous good quantum number, so I can just associate t with ky in the previous models. And then I can easily come up with toy models for Chern insulators, because these are Chern insulators. So Chern insulators are the ones where the bulk Chern number is non-zero. As a consequence, they will have these edge states. So here I'm plotting the spectrum of a very similar Hamiltonian as before, but instead of t, I write ky, the wave number along the y direction, and this is how the spectrum looks like if I take a Hamiltonian with a topological invariant being 1. I have one edge state propagating on one edge. As you see, this blue one is propagating on the left edge, this red one is propagating on the right edge. So if I actually make a ribbon, this is how it's going to look like, and also I depict now these modes which are seen here. So these are now modes localized in space. They live in a certain energy window, but in that energy window nothing else is living, so there's a gap. Only these two states are living in that energy window. One is going, let's say, upwards on the left edge, and the other one is going downwards on the right edge. Whether they go upwards or downwards, that depends on the group velocity, of course. The group velocity is just the derivative of the dispersion relation with respect to the wave number, and that's opposite for the two states. Okay, if you think of these models in terms of two-dimensional crystals, then it's quite obvious from the picture that to get such a crystal, to get such a sample, you will require time reversal symmetry breaking, simply because this guy is going upwards and there is no counterpart of it which will go downwards. So in that sense, it's clear that to have this kind of states, you have to break time reversal symmetry. Sometimes these kind of systems are called Chern insulators. Mostly they are called Chern insulators because there's this Chern number which is associated to them. But also sometimes they are called quantum anomalous Hall insulators. So notably, when the B field is 0, then typically people use this phrase quantum anomalous Hall insulator for describing these kind of setups. Of course, if B is 0, then why is there any time reversal symmetry breaking? The answer is that you have to introduce that by some magnetic components of your setup, magnetic impurities or magnetic layers. You have to achieve some kind of time reversal symmetry breaking without B field to get a quantum anomalous Hall state. Okay, so the important point, the message here is that once you put your Fermi level in the gap in such a two-dimensional material, then the edge electrons can't be backscattered. Why am I saying that? Well, let's imagine that I'm occupying this right-going state, this blue one, which is localized on the left side. It moves along the edge, and it meets a scatterer somewhere, an impurity. I'm claiming it cannot be backscattered. Why? Well, because at least elastically it cannot be backscattered, because elastically the only thing it can do, it could go into the other state which has the same energy, this red state, but it's very inefficient because this other state is localized on the other edge. Okay, so the two facts, the fact that these guys live in the band gap of the semiconductor, and the other thing is that they are very much far apart from each other. These two components ensure that backscattering is very low. So these channels, even though I'm showing you a case when this is an ordered sample, there is no disorder in this, even then, from this picture, it's obvious that even if you introduce some scattering, the scatterers will have a hard time to actually scatter these states. So we have very good conductance along this edge and also along this edge to the respective directions. Actually, it's going to be a quantized conductance. So maybe you are familiar with Landauer-Büttiker formalism. In that, it's a clear result that if you have a single conducting channel, a transverse channel in such a device, then it will lead to a quantized conductance. The conductance quantum is E squared over H if you don't have spin degeneracy, and 2E squared over H if you have spin degeneracy. So the existence of these states is indeed can be probed via transport experiments. If you have such a device, you should measure the conductance or some kind of related quantity, and demonstrate that it should be able to demonstrate that it doesn't really depend on the disorder concentration. Okay. Yeah.
Just a question.
Yeah.
Okay, but the dark scattering is quite protected. But if you imagine you have some defects on the then this Planck diagram doesn't hold anymore, at least locally, and then you have KK prime scattering possible with the same projection of K. I agree, but yet the K will change, and then you probably quantization will not be perfect. Because this
So what I would say that
diagram we wrote, it comes from the perfect alignment of this horizontal chain, right? And then you repeat it just in a y direction. But imagine in the middle you have one atom missing, which is on the edge of the on the blue side. Locally, if you calculate the same chain, you will get a little bit different crossing, a little bit different because you have not 10 but 9, okay, levels, so locally, and then when you connect this defectors chain to others, then you will have a sort of defect, and it means that this scattering is possible. It's not back scattering, of course, forward scattering, but with different K.
Okay, okay, I see your point. So you say that I take, let's say, this blue state, and you're saying that I could be scattered from this state to some other point on the.
It's the same, but a little bit shifted. Your X-like crossing, or if you will Dirac crossing, will just leave a little bit depending on where you are.
Yes. Yes, I would say that in sort of a naive scattering picture, I think that doesn't hurt. So the key, so one picture you can have is that you have this localized scatterer, and before that and after that you have a nice crystal. Yes. Then energy must be conserved. So as long as it is elastic scattering, energy must be conserved in total. So if you have an incoming electron with a certain energy, it must go out with the same energy. And no matter what the dispersion looks like in the scattering region, this must hold. So in that sense, I would object to your suggestion.
If the scattering elastic,
Yes,
yes.
and I would say that there's no protection against inelastic scattering. So I think that's an important thing, that for example, in a quantum Hall device, I mean, you must cool it down. I think in high temperature, one thing is that you have more phonons, for example, they can scatter. So a phonon, if you have many phonons, you are in this state, you believe that you are protected, but a phonon kicks you up there, there's no protection, right?
In quantum Hall device, the nature protects because of the deflection of the bands at the edge, the physical edge. And then, in fact, your state is not at the edge, it is inside the matter, but it is inside the gap.
Yeah, that's the point. So it's not that important exactly at the edge. The point is that it should be in the gap, it should live in the gap, and if there are no available states in the gap to be scattered to, only the other end, then that's very inefficient to be scattered. Okay, good. So the question is, do they exist? Do these chiral modes exist in reality? So these are called chiral modes, I forgot to say. And one instance, an experiment was done on Monday. So we have observed a chiral edge mode at the dinner table on Monday. This is a self-serving table, and everybody was queuing and going into this direction. So it's like a chiral current. I was considering writing this up. So the picture was taken by Szabolcs. I was considering by submitting this to, this is my first experimental paper, by the way. Journal of Portuguese Gastronomy, high impact factor, you can imagine. This is going to be a single author paper. So there were many contributors, most prominently Szabolcs, who took the data, but I thought that I would submit it as a single author paper, and I will acknowledge most valuable help for Szabolcs and also the audience who were taking part. Okay, so this is a real life experiment about chiral modes. But actually, sort of another more abstract experimental setup looks like this. So you actually, a theorist's picture of an experiment with a Chern insulator is this, so that you have a ribbon, and then you just contact the two ends. You ground one of them, you put some voltage on them, and then measure the current. And the claim is that because you have, let's say from up to down, you have this single channel which is conducting, you will have the corresponding quantized conductance E squared over H, which is measured in this setup. My understanding is that hardly anyone does experiments measuring this thing, maybe due to practical reasons like contact resistance and so forth. So most of the experiments I know are done in whole bar samples and not in 2-terminal samples. So these are usually 6-terminal samples. And one experiment, I think maybe this is the first demonstration of this of a measurement of this quantum anomalous Hall effect is shown here. So this is from 3 years ago from an experimental group in Beijing. I try to briefly describe. I don't have a very deep understanding of what's going on, but I try to describe what I understand. So the material itself is this one, this gray thing here. This is a slab. This material, so this would be a compound which is on itself a 3-dimensional topological insulator. I think an important ingredient here is that it has strong spin-orbit interaction. But you also have to have a quantized anomalous Hall effect. You also have to have a time reversal symmetry breaking at 0 field, and I think that's supplied by these magnetic ions, chromium ions. So the picture is this one, that even at 0 temperature you might have a ferromagnetism at low temperature. So these chromium ions are polarized, and they will exert an exchange field essentially on the electrons which are living in this two-dimensional slab. And then one can, I think the experiment is that they current drive this setup. Okay, so this is where you see the 6-terminal setup. So you have the source and the drain. Okay, so what the sample is this light gray thing. So the sample is the light gray thing. And then you send current between the source and the drain. And then you also have these contacts, 1, 2, 3, 4. And you also have these sort of small windows where the electrons can go. And so this is a 6-terminal setup. And you send the current through. And what you can measure here is you can measure the longitudinal conductance. So you measure the voltage difference between these two, dividing the whole current with the longitudinal voltage difference, giving you a longitudinal conductance or resistance. And you can also measure whole conductance. So you send in this current and you measure the transverse voltage, so the voltage between this top left and this bottom left electrodes. So that's gonna, if you divide the voltage measured there with the current sent through, then you get the whole conductance. And I'm not going through the details, but simple Landau-Büttiker pictures tells you that the whole conductance should be quantized in the same units, as I said before, E squared over H, or H over E squared is the resistance quantization. And I think these plots are illustrating this. So if you fine-tune your system, so it's believed that the system is a semiconductor, where the gap is opened due to a number of mechanisms, including this ferromagnetism. So there is a small gap, and you can tune with a gate voltage. You can tune the electron density or the carrier density in this slab with gate voltage. And here what you see is the measurement of this. Let's focus on the blue curve. So the blue curve is the whole resistance measured as a function of gate voltage. And what you should see is that there is a range of gate voltages. It's very narrow, where indeed we have this quantized value of rho y x. So this is the whole resistance. So it gets a quantized value in a window of gate voltages. So the picture is that when your gate voltage is in this window, then your Fermi energy is indeed between the valence band and the conduction band, and it's going to be the Fermi energy is going to be sort of filling the edge states, and these edge states will give you these conduction features which are measured here. All right. So this is just repeating the conclusion of this third part. So the conclusion about the 2D Chern insulators. If the bulk has non-trivial topology, then the edge provides quantized conductance. This is the second instance of bulk boundary correspondence, when the bulk invariant, the Chern number in this case, is predicting the behavior of the edge states or number of edge states. Okay, and the last thing I wanted to talk about a bit is quantum spin Hall insulators. So here the message, a single sentence message is this one. Even time reversal symmetric 2D materials can have robust edge states providing quantized conductance. So far, talking about Chern insulators, I was saying that to get that physics, you need time reversal symmetry breaking. But here I'm making the claim that even if you don't break time reversal symmetry, you can have edge states and robust quantized conductance. And I don't want to go into much detail. So of course, one important detail or concept is time reversal symmetry. I don't want to be more general than any physics textbook about this. So if you have spins, electrons are spinful. Usually the time reversal transformation is represented by this unitary, anti-unitary operation. So its complex conjugation is K, and sigma y is the Pauli matrix, which is acting on the spin. So this is now not sublattice but spin. You call your system time reversal symmetric if this time reversal operator commutes with the Hamiltonian, which means that if you transform your Hamiltonian with this time reversal operator, then you get the Hamiltonian itself. Usually, the system, electronic system is time reversal symmetric if there is no B field and there is no magnetic order in the system, then you have a time reversal symmetry. And an important consequence of time reversal symmetry is Kramer's degeneracy. So here, again, Kramer's degeneracy is a consequence of time reversal symmetry. As we've seen, there was chiral symmetry, also chiral symmetry had consequences. This is similar in the sense. So now, if you have an eigenstate with energy E for a system which is time reversal symmetric, then it follows that if you time reverse the state itself, that's going to be a new energy eigenstate with the same energy. Okay, and it's going to be a different one from the previous one. So you take the state, you time reverse it, then that's going to be orthogonal to the original one. Okay, so that means that every state, every energy eigenstate in a time reversal symmetric system has its pair, which is different from itself, and it's connected by time reversal. This is called Kramer's degeneracy. Generically, this is a two-fold degeneracy, so every state is two-fold degenerate because of that reason. This sort of statement can be converted also to momentum space. In momentum space, it connects a positive momentum k with its negative counterpart minus k. So the Kramer's pairs are located there. And an easy way to construct a model showing time reversal symmetry and edge states is just to take two Chern insulators with opposite Chern numbers, and then you will have, if you do it cleverly enough, then you will have propagating modes on both edges in both directions. So that's done here. So this is called the Bht model, which is named after Bernoulli, Hughes, and Zhang. This is just really, you can construct it by taking two Chern insulators and coupling them in a meaningful way. And what you see is that, again, you have the gap, and in the gap, you have the edge states. Again, color coding is referring to the position of the edge states. So you see that red is present on red. So there's a red, there are two red states, one going to the right and one going to the left. Both of them are localized to one edge, and the blue states are again also there. They are also localized on the other edge. But on both edges you have states. So the simple sort of extension of the Chern insulator picture for this case is this one. So this was the Chern insulator, which is sometimes called quantum anomalous hole insulator. You have chiral states propagating into a certain direction, here clockwise around the sampling edges. And then if you construct such a quantum spin hole insulator, then this is the picture that you have counter-propagating edge modes on both edges, and they have different spins in this example. So that's spin conservation is not a requirement, but in the simplest models, the spin configuration is very simple. Let's say the outgoing state here has a spin up, so pointing outwards from the screen. Here it's pointing inwards, and the other way around there. These sort of states usually are called helical edge states, as opposed to chiral edge states, which are the ones in the Chern insulators. And then one result is that, as we have seen that for Chern insulators with Chern number 1, we have this quantized conductance expected in experiments, E squared over H. Without disorder, if I just look at this plot, without disorder, I would say immediately that probably then the conductance of a quantum spin hole insulator is just double of the conductance of a Chern insulator, because I have now on both edges I can conduct to a given direction. The important claim is that this holds not only in the absence of impurities, but also in the presence of impurities, if those impurities are respecting time reversal symmetry. So if I have magnetic impurities, like localized spin impurities on the edges, along the edges, those do not conserve time reversal symmetry, so those are dangerous. They can cause backscattering between, let's say, this upgoing state and this downgoing state. But if my impurities are non-magnetic, it's just potential scattering, then as long as they are time reversal symmetric, they cannot induce scattering between these states. And thereby, even in a disordered case, you will retain a quantized conductance, which is quite a remarkable prediction regarding the fact that we know that in disordered systems, Anderson localization is often preventing efficient transport. And I think in 1D, Anderson localization is setting in as soon as you start to switch on disorder. And this is a very, in that sense, it's a sort of a counterintuitive result that you can engineer a quasi one-dimensional structure where Anderson localization is not efficient. So even if you put disorder, it will not localize your particles, but you will have a nice conductance. Okay, and of course, I mean, okay, if I want to summarize these quantization rules for these two different types of models or materials, quantum anomalous hole is robust against many things. I was not listing inelastic scattering, for example. I should have put a red cross for inelastic scattering, but it's robust against changing the chemical potential within the gap. It should be robust against sort of continuous deformation of the Hamiltonian, if that's a thing you can do in experiments. It's not that easy, I guess, with real condensed matter samples. These are robust. These edge states, the conductance quantization is robust against time reversal symmetry disorder, and also against generic disorder, as long as that's sort of elastic. And the difference in quantum spin hole is that this conductance quantization is not robust against the generic disorder. As I said, if you have, for example, magnetic impurities, then they will break down this conductance quantization. Okay, and finally, I think this is the last slide, a brief summary of the first experiment demonstrating quantized or quasi-quantized conductance in such devices. So this is from Würzburg, from the Molenkamp group. This is a complicated semiconductor heterostructure where maybe the key part is this mercury telluride well, which has a thickness. This thickness is an important parameter. So the claim is that if this thickness is larger than a certain critical thickness, then it's going to be a two-dimensional quantum spin-Hall insulator. And they measured in this 6-terminal geometry again. And here, the quantity which they measured was the longitudinal resistance, but it's measured in a 4-terminal way, in a sense that they send in a current from 1 to 4, from source to drain, and then they measure the voltage between 2 and 3. So that's what can be called the longitudinal resistance. And again, from simple Landauer-Büttiker type picture, it comes out that conductance should again be quantized. And this is the quantized value here. And these are now different samples, different temperatures. And okay, so if this is a quantum spin-Hall insulator, then this should be sort of a constant here. Okay, this is a signature that this might be a quantum spin-Hall insulator. Certain checks can be done. Of course, this is now the gate voltage again. And one check is the robustness of the quantization against the gate voltage tuning. As long as we are in the gap with the gate voltage or the chemical potential, we expect to have this quantization. That's one check which is easily done in experiments. Another check could be to somehow continuously deform the Hamiltonian. I think that's quite demanding in an actual experiment. What they did, nevertheless, was doing the same experiment with different width of this quantum well. And as I said, the prediction was that if this is thicker than a critical thickness, then it's going to be topological, holding edge states. If it's thinner, then it's not going to do that. And the observations are not shown here, but they are shown in the paper, so they are sort of in line with these expectations. That's also nice. Right. Okay, so I think this does conclude my lecture, if I can. Maybe I cut down the last slide. Okay, but so just summarize in words. So my aim with these two lectures was to really give an introduction to topological insulators in 1D and 2D by trying to single out the most simple examples where you can see some topological features in band structure theory. And the key point was that in 1 dimensions, chiral symmetry gives you this interesting effect that you have edge states which are robust against disorder as long as they are respecting chiral symmetry. This line of thought is brought along for one-dimensional topological superconductors where people try to build qubits based on these zero energy modes. And then in the second talk, I was trying to illustrate, again, using simple models and the picture of adiabatic pumping in one-dimensional materials, how you can arrive to a boundary correspondence for two-dimensional Chern in insulators. I tried to demonstrate that there was measurement, there were measurements of this effect, even in zero-magnetic field. And then in the end, I will try to argue that by doubling a Chern insulator in a time reversal invariant fashion, you can come up with systems where you have time reversal symmetry, but nevertheless they show quantized conductance along the edges because the edge states are robust against scattering. Okay, thank you very much for your attention.
We have a few minutes for questions.
Can you say something about what happens with the local